sections, your edges.
Great. Thanks, Hugo. OK. So I'm going to be telling you all today about a recent paper that I wrote with Ankar Parakar and Patrick Hayden, in which we investigated some properties of this geometric object called an entanglement wedge cross-section. It's something that a lot of people have been interested in. For the purposes of this talk, I'm not going to assume that you have any familiarity with the entanglement wedge cross-section. I'll give an introduction to what these things are and why we might be interested in them. And then I'm going to tell you some new properties that we proved, and I'll give you an interpretation of these things in terms of holographic entanglement. So that's the general idea of the talk. I'm going to start off by giving sort of just a general discussion of what we might call bipartite versus multipartite entanglement. I think this is a really important idea, understanding what entanglement patterns are like and what it means for an entanglement pattern to be multipartite. It's not something that a lot of people in our community encounter on a daily basis, but I think has important consequences for holography, so I'll try to convince you of that. Then I'll introduce these cross-sections. I'll talk about their duals and holography. I'll give you our main technical result, which is a geometric bound on these duals in terms of this thing called an edge count. And then the rest of the talk is mostly just going to be QI. I'll tell you what I think our main technical result means in terms of a quantum information language. And if I have time, I'll tell you how we prove our main technical result, but I imagine we will not actually get to that. Feel free to interrupt me at any time for questions. Happy to be at Berkeley. Happy to be talking. So let's start with a little discussion of bipartite entanglement. Now, in honor of, I guess, Lenny Susskind, or in a tribute to Lenny Susskind, I'll call my first section, Ryutakinagi is not enough. So what do I mean by that? Well, as a preliminary question, we might ask, why, as quantum gravity theorists, are we interested in entanglement? As a preliminary answer, you might say anyone who's doing any kind of quantum physics should be interested in entanglement. It's the thing that makes quantum physics quantum. So, if you're doing quantum physics, you ought to try to understand the entanglement structure of whatever you're studying. But the discovery that really made the field of holographic entanglement take off was this Ryutakinagi formula, which I imagine most of you have seen before and many of you have written many papers about. So I'll be pretty brief in reviewing it. The Ryutakinagi formula is an entry in the ADS-CFT dictionary that relates an entanglement entropy, which is something you compute in the field theory side of the duality, to the area of a particular surface in the gravity side of the duality, divided by 4g. And there's a prescription where you minimize over all areas, you minimize over the areas of all surfaces that satisfy particular boundary conditions. There are many generalizations of this that I assume many people in the audience are familiar with, all the way up to this fully covariant quantum extremal surface formula. We won't need to think at all about that for the purposes of this talk. It's going to be enough to think about the plain old RT formula. So the typical sort of sketch that we draw to understand this formula is I've drawn here a t equals 0 slice of ADS3. So this is like a hyperbolic disk. And I consider perhaps some boundary interval A. And the surface, gamma, that appears in this equation, computing the entanglement entropy of A, is just going to be the geodesic linking these two endpoints, the bulk geodesic linking these two endpoints, which is gamma. OK. So the simplicity of this formula, a very simple bulk construction being related to a very fundamental boundary entanglement quantity, is partially responsible for this slogan that you might hear, which is space-time emerges from entanglement. If you haven't read it, especially for the younger students, I really encourage you to read Mark van Ramstonk's paper, Building Up Space-Time with Entanglement. It's the one that really sort of set forth this idea that space-time is something that emerges from entanglement. It takes the Ryutakinagi formula as its starting point and does thought experiments that I think make that idea very compelling. But if we really believe that space-time emerges from entanglement, then somehow this formula isn't enough to tell us how space-time emerges. And the reason for that is that knowing all of the entanglement entropies of a state isn't enough to tell you how the state is entangled. Even if I know all of the entanglement entropies of all the subsystems, there are still interesting properties of the entanglement of the state that you won't know about. I'll give you an explicit qubit example in a moment. But before I do that, let me just give you some intuition. What I'm going to tell you is that the entanglement entropy is something that bears witness to what we might call bipartite entanglement. So what does that mean? Well, if you ask any quantum information theorist what the entanglement entropy means, they'll tell you the following. Imagine that Alice and Bob each hold some set of qubits. So over here's Alice, over here's Bob. Let's say they each have 10 qubits. And the 20 qubits that they hold together are in some complicated entangled state. I'll represent that by drawing some jagged line here. They hold some qubits that are entangled. Now, what does the entanglement entropy tell you? It tells you how well Alice and Bob can convert this complicated entangled state into a simple one. So let's say Alice and Bob want to do some local operations on their qubits and convert this entangled state to something very simple. What these lines are supposed to represent is a maximally entangled state, right? They had, 10 qubits that were entangled with another 10 qubits in a complicated way, but they want to convert this so that each qubit that one of them holds is maximally entangled with one of the qubits that the other one holds, right?
So they were already maximally entangled to start with?
They weren't maximally entangled to start with. The final number of qubits here might be smaller than the number here, right? So yeah, and in fact, this is a good point. The degrees of freedom that they hold at the end might be related to the original degrees of freedom in a very non-local way, right? The degrees of freedom that they're working with at the end might be linear combinations of their original, or non-local combinations of their original qubits. And those are the things that are maximally entangled at the end of the day. But what the entanglement entropy tells you is how many maximally entangled states they can expect to get, right? So it's more subtle than that. I mean, like, yes, the statement I said is actually technically only true if you have a large number of copies of the system and you take a limit, right? What I've described is what's called a one-shot distillation. The entanglement entropy actually controls what you might call asymptotic distillation, but I'm not going to dwell on that for the purposes of this discussion. As for your question, you can imagine you can do any quantum channel you like, right? So Bob could bring in a bunch of qubits and interact them in some non-local way and then throw out a bunch of them and end up with 3 qubits that, how do you relate those qubits to the one he started with? Maybe they're qubits that were in the auxiliary system that he brought in, okay? So I think from this description, and I will emphasize Raphael's question, which was just that, as I've described it, this isn't technically true. What the entanglement entropy tells you is how well you can do this process on average if you try to repeat it a large number of times. But like I said, we won't dwell on that for this heuristic.
I thought that the entanglement entropy tells you how well you can do this when you have many copies of the system.
Yes.
From repeating it.
No, well, actually, yes, you're right. It's not repeating because, absolutely, thank you, Raphael. You take a large number of copies of the system and you can act on them all at once, so it's not just repeating. And you try to do this in some sort of limiting sense. The von Neumann entropy tells you the rate at which you can maximally expect to do this.
I mean, for a generic initial state, you can't do anything at all, right? One-shot instruction.
For a generic one, no, probably not. For a state with a good smoothed entropy, then you can. Okay. So I think it should be clear why I call this a bipartite measure of entanglement, right? Because what it tells us operationally is how well Alice and Bob can split their qubits into simple maximally entangled things that they share just between the two of them. But we might ask a different question, which is what if, before they try to do this distillation, Bob hands off some of his qubits to Charlie? So now Alice, Bob, and Charlie share some tripartite entangled state. And imagine now they try to do a similar thing, right? They try to distill their qubits into some simple maximally entangled state. Well, now we're forced to ask the question, all of these qubits, one side of which was held by Alice, where's the other side of those qubits, right? We might imagine that after this distillation procedure, some of the qubits are shared with Charlie, some of the qubits are shared with Bob. But because I said that this distillation was something non-local, we might also expect that some of Alice's maximally entangled pairs are shared in some non-local way between Bob and Charlie. Okay? And Alice. Yeah. Right.
And why did you not draw any lines and just go between Bob and Charlie?
Oh, because I'm trying to do a bipartite distillation between A and the group BC. Yeah. I'm just trying to emphasize that, this tells us how the block of Alice's qubits is entangled with the block of Bob's qubits, but it doesn't tell us how Alice's qubits are entangled with the individual qubits in Bob's. And what is that sort of non-local structure like? Okay? So let me give you an example. I think this is worth meditating on because it's not something people think about a lot. Also, everything I said here is supposed to be very heuristic, so if you don't feel like you understand it at a technical level, that's good because there's no technical level for what I've just said. This is a heuristic description. So let's.
Sorry, what represents the intersection of the line?
Yeah, that's supposed to represent that Alice is holding one end of a maximally entangled pair, but the other hand isn't one of the local qubits held by Bob or Charlie. It's something that is non-locally distributed between Bob and Charlie. Right? I'm only emphasizing there's some complicated structure here. Okay, so let's look at a simple example for 3 qubits where all of the entanglement entropies are the same in the 2 states, but the tripartite entanglement structure is meaningfully different. Okay, so I have 3 qubits, A, B, and C. And I'm going to define for you 2 different states on these qubits. The first one is a very famous state in quantum information theory called the W state. It's not really that important what it is. I'm only using it to illustrate an example. And the other state is going to be a state I'll call G, because it's sort of like the GHZ state, if you've heard of that, but with a slightly different weighting. Okay. So these are 2 different perfectly legitimate states that I could define on 3 qubits. And if you go through the calculation to compute their reduced density matrices, you'll find something interesting. The reduced density matrices of either of these states on a single site are exactly the same. Okay? And what that means in particular is that all of the entanglement entropies in these states are exactly the same. Right? Because these states are very symmetric. The only entanglement entropies I could compute might be 1-party or 2-party entanglement entropies. And those have to be the same by purity of the state. So if the reduced density matrices on a single site are the same, all of the entanglement entropies are the same. Okay? But these states are actually very different from the perspective of quantum information theory. And the reason for that, I'm not going to actually do the calculation because I don't think it'll be instructive. I'll just tell you the result, is that I might ask what happens if I throw away a single qubit. So let's say I throw away the first qubit and I look at the 2-party state of W versus the 2-party state of G. What you're going to find, if you do this calculation, is that the 2-party state of G is completely unentangled. It's a probabilistic mixture of product states, meaning there's no entanglement. Whereas the 2-party state of W is entangled. It can't be written as a probabilistic mixture of product states. There's some entanglement there. Okay? So even though all of the entanglement entropies were the same, these 2 states are very different because if Alice, Bob, and Charlie share either the W state or the G state, in one of them, Alice and Bob will be entangled, while in another one, they won't be. Okay? Even though all of the entanglement entropies are the same. Okay? So I think, this is emphasizing for us why we really need to think about tripartite entanglement structure when we think about holography. An analogous thing we might imagine doing here is if we look at that complementary boundary region to A, and we split it up into 2 regions. And we might start asking, how are the correlations between A and its complement divided between those 2 regions, either locally or non-locally? These are interesting questions. So as a way to try to start to study that, many people now, have started looking at these quantities called cross-sections. I think the philosophy here is very simple. The Ryu-Takiyanagi formula tells us that sort of like the simplest bulk object we could imagine to associate to a single boundary region is this minimal geodesic. And it's equal to this simple boundary dual, this entanglement entropy. So the next thing we might do is say, well, let's look for a simple bulk object that we can associate to two boundary regions and look for a bulk dual. And maybe this will give us some information about tripartite entanglement structure. So that's what we do. I'll tell you how the cross-sections are defined, but I'm really just going to give you two examples. I'm not going to give a formal definition. I think it'll be pretty clear. So let's look again at ADS3, t equals 0. And let's look again at a single interval on the boundary. But then I'm going to declare that Bob holds this interval on the other side of the boundary. Okay? And I'm going to call the complements of A, B, C. Right, so now I've given some tripartite division of this pure state. And how do I define the entanglement wedge cross-section? Well, the first thing I do is I look at the entanglement wedge of A and B. And I'm going to assume that these two are large enough that the entanglement wedge is this connected thing. Okay? And the prescription for defining the entanglement wedge cross-section is that I look at all possible cuts of the entanglement wedge that divide this wedge into two parts, one corresponding to A and one corresponding to B. So for example, this might be such a cut. It goes between the two pieces of the AB minimal surface, and on one side of it lies A, and on the other side lies B. Here might be another such cut, right? And the prescription is that I minimize over all of them. And by symmetry, it's very simple to see what that is. It's going to be some geodesic like this that intersects the minimal surface at right angles. Okay? And I'm going to call it sigma A colon B to emphasize that it's a quantity associated with this bipartition A and B. Okay? If you want a formal definition, you can look at many papers. I hope that this is at least fairly intuitive. Let me give another example in case it's not especially clear. This example will be important later. Let's imagine we have a geometry that is a three-boundary wormhole. So I'm going to label the mouths A, B, and C. And I'm going to assume that A and B are large enough that the minimal surface of AB is this throat of the C wormhole. So in particular, we're once again in a case where the entanglement wedge is connected, right? It's this whole region down at the bottom. And what's the entanglement wedge cross-section going to be? It's going to be a geodesic that starts here, goes down the front of the wormhole, loops around the back, and intersects gamma AB in the back, again, always at right angles. And this will be sigma A, B. Okay. Any questions about this construction? Obviously, it can be generalized to covariant cases. Quantum generalizations are actually a little subtle. I might talk about that in a few minutes. Good? Okay, so let's talk now about the boundary duals of these things. These quantities, these cross-sections, were originally introduced in two simultaneous papers that proposed they were dual to a boundary quantity called entanglement of purification, which I will not define for you anywhere in this talk. I'm just going to say maybe there's a proposal that this thing called EP, which is a boundary entanglement quantity of some kind, is equal to the area of sigma AB over 4G, which, to save space, I'm just going to call EW. Area over 4G. Okay, it's not actually important for the purposes of this talk that you know what EP is. All you need to know is that there is this entanglement quantity you can define purely in the field theory that people proposed was dual to this quantity.
I have a dumb question. Why are you calling it EW since you already called it EP?
Oh, I'm calling this thing EW, because I'm going to use it in another formula. So I'm defining EW to be the area of the cross-section over 4G. There is a proposal which is EP equals EW. But EP is something that's defined on the boundary side. Okay? Doesn't matter what it is. I'm only saying this for completeness so that if you ever look into the literature, you'll recognize these things. There is a more compelling argument, so I'll say definitely rather than maybe, for a different proposed dual. which is called the reflected entropy. And I will actually define this for you in a few minutes. For the moment, just say, this is something you can compute in the boundary theory, and we'll learn what it is in a little bit. And the proposal is that this thing is equal to 2 EW. OK. These two things could be consistent. I'll just say a couple of words, which is that in order for these two things to be consistent, we need it to be true that in holographic states, SR is equal to 2 EP. That's not true in general quantum states. You can find violations. But it might be true in holography. There are some arguments for it. We can talk another time if you're really curious. I'll tell you that this is much more compelling because it comes from the gravitational path integral. There's a path integral argument that Dutta and Faulkner made. Maybe I'll write their names. I would write all of the names for EP, but there are like 8 between the two papers. So there's a gravitational path integral argument for this one. OK. So in the next section of the talk, in section 3, I am actually going to tell you what this quantity is. And we'll talk about it as a quantum information quantity. For the moment, I ask you to just sort of bear with me by saying, this thing exists, whatever it is. And I'll tell you some of its properties. OK? So there's a very important property of either of these correlation measures, either of these entanglement quantities, either EP or SR. And that's a relationship with this thing called mutual information. Just give me a second. I don't want anyone to think those are Feynman diagrams. OK, so here's a theorem. And I'll explain what this means. 2EW is bigger than or equal to IAB, where this is the mutual information, defined as SA plus SB minus SAB. Now, what do I mean by in either case? Well, whichever of these dictionaries I choose to use, it's possible to prove this inequality purely in quantum information theory. So it's true that for any quantum state, twice of EP is bigger than or equal to mutual information. It's true in any quantum state, SR is bigger than or equal to mutual information. It's also possible to see this directly in holography, where we actually treat EW as a geometry quantity. And I'm going to give you this short proof because I think it's very instructive. OK? So let's, for our proof of this in holography, let's do proof by example. Let's look just up at that first example I drew up there of an entanglement wedge cross-section for 2 intervals. OK? And so I'll write example. And let's write out, well, here, let me actually, I want to add 2 surfaces here. I want to add the Ryutaki-Nagi surface for A and the Ryutaki-Nagi surface to B, for B to my diagram. OK. So let's write down this quantity. Well, let me write down sort of all of the entanglement quantities that will show up here. Pictorially. The entanglement entropy of A, I'm going to write as this curve, because it's supposed to represent the area of that left blue surface. I'm sorry I chose such a dark blue. Can you distinguish it? Right? The entanglement entropy of B, I'm going to write like this curve, because it's supposed to be the area over 4G Newton of the corresponding surface on the right. SAB, I'm going to write like this. And EW, I'm going to write like this, because it's supposed to be the area over 4G Newton of the entanglement wedge cross-section. OK? So let's use this pictorial language to write down the quantity 2EW minus I. And I'll throw in a 4G Newton over here for completeness, so we can really just think of everything I'm writing on the right-hand side as areas. All right? So let's see. I have 2 copies of EW. So that's 2 copies of this vertical line, minus S of A minus S of B plus S of AB. Okay? Now I can choose to cut and paste these surfaces however I want. Right? All I'm doing here is I'm computing an area. So I could choose to, add half of this surface and then add the other half of the surface in a different term. I can regroup these in a way that's going to be instructive. So the way I'm going to do it is I'm going to take sort of the left half of this surface and tack an entanglement wedge cross-section on there. And I'm going to take the right half of this surface and tack the other piece of the other copy of the entanglement wedge cross-section on there. So these terms that I've written here take care of these two entanglement wedge cross-sections and this surface here. Any questions about that? OK. And then I'll just keep what's left over, which is minus this surface and minus this surface. OK? Now, the reason that this way of rewriting the equation is instructive is because this surface here is the Ryutaki-Nagi surface for A, which means it's minimal in its homology class. This surface that I drew here is in the same homology class, right? So it has to have greater area, or no smaller area, right? And the same is true over here. So these two parenthetical terms are individually non-negative, just by the definition of the Ryutaki-Nagi surface. Yes?
I'm convinced by this, but yet I'm confused by something that I can't reconcile with it, which is if I dial the size of A and B so that we're just at the phase transition, I would have, so then this should be 0, right? This initial command should be 0. And yet it seems naively like the entanglement wedge cross section is not 0. Oh, sorry, that makes sense because it's then bigger. Yeah. Sorry.
Yeah. You also end up with ambiguities at that phase transition anyway. Like, is the reflected is the entanglement wedge cross section 0 or the smallest interval, right? Yeah. But yes, it's good. It goes in the right direction. Yeah. I've had plenty of these thoughts while I was working on this project, so don't feel too embarrassed. Okay. So is there a clock in here? I want to know how I am on time. Oh, great. Okay, cool. So I'll just make a comment, which is this was a purely classical argument. Okay. This is something that we knew was true for the holographic duals. And now we have sort of an obvious reason why it's true classically in the bulk. You might also want to extend this to quantum-corrected versions of these formulas, right? I'll only make the comment, which is that I don't know how to define a quantum-corrected version of EP in the bulk. I know how to define a quantum-corrected version of SR in the bulk. And with the extra bulk entropy terms that you incur, you can also show this same inequality. It's a little more subtle. We do it in an appendix of our paper. It uses quantum maximin. That's just an advertisement if you are curious about these kinds of arguments in a more general context. OK. But why did I spend so much time making this argument for you? Because the difference of these two quantities, 2EW and I, turns out to have very compelling and very important consequences for quantum information. And this is due to a paper by Berkeley alumni, beloved Berkeley alumni, Akers and Roth, who showed the following as a theorem about quantum information states. And I'll write it, and it might not make immediate sense, but I'll have to explain it. So they said if 2EW minus I is equal to order 1 over g Newton, then the pure state, ABC, has order 1 over g Newton tripartite entanglement. Anyone who's very good with notation should probably object that what I call big O here is really like theta or omega. I never remember which one is which. What I mean is that suppose that this quantity has a contribution at order 1 over g Newton. Okay? So in particular, all of these formulas are supposed to be understood as perturbative expansions in g Newton. If this thing is non-zero at the leading order, then there is a corresponding amount of tripartite entanglement in the full boundary state. Okay? I won't tell you how they, well, I will tell you how they prove this. It's actually quite easy. They prove the converse. They generate like a generic form of a bipartite state with a parametrically small amount of tripartite entanglement. And they compute, well, okay, this might be Raphael's question. This is true for either of those boundary duals stated above, okay? So if I assume the dictionary EP is equal to EW, then as a quantum information statement, I can say EP minus I having a large gap means there's tripartite entanglement, parametrically large tripartite entanglement. Or equally well, if I assume the other dictionary, SR is equal to 2EW, then a large gap between SR and I parametrically is going to imply a parametrically large amount of tripartite entanglement. That's your question?
Two questions. One is just to confirm, you're defining C as the complement of A and B?
Yes.
Okay. And how are you quantifying the tripartite entanglement?
Yeah. So what they do is, you can only quantify it parametrically. So what they do is they say, imagine you have, I don't want to, they do something like this. I don't want to claim that I know exactly how it is. They say, imagine I have some state psi 1, A1, B1, psi alpha, A1, B1, psi beta, A2, C1, psi gamma, B2, C2. So they split the A, B, and C Hilbert spaces into bipartite tensor factors. And they construct this state, which would be a state that we would have. So like A is supposed to be decomposed into A1 and A2. B is supposed to be decomposed into B1 and B2, and C into C1 and C2.
So that means you can always write a state like that?
They say a state of this form, it's manifestly good to call a state of this form bipartite. Like all of the correlations in this state come from bipartite correlations between A and B, A and C, or B and C, right? And then they act with some unitaries that do a little bit of mixing. I don't remember exactly where the unitaries act. Maybe they mix, I think they mix A1 and A2, B1 and B2, and C1 and C2. But they're not allowed to do anything that mixes the A's, B's, and C's. And they call such a state bipartite entangled, right? But what they show is that if you add on a small state chi, which is on, say, A3, B3, C3, right? So actually, let me make a comment. Let's imagine I hadn't put this chi here. So I had some state that was like bipartite entangled. Is this too?
This is going much too fast.
Okay.
You're introducing a lot of new notions here that you didn't prepare us for.
Okay.
Are we taking A to be partitioned into A1,
Yeah.
A2, and A3?
Yeah. So let me.
And so on?
The
I think you already, if A is partitioned to A1, A2, B is B1, B2, and C is C1, C2,
Does not also be free, right?
yeah. So let's ignore that for a moment.
in such a way that you can write the state in this form
Yeah.
with the psi alpha, psi beta, psi gamma to be pure. If the state can be written in this form for some partition of A and B and C into 2, then this is purely just represented just by bipartite entanglement between A and B, A1 and B1, A2 and C1, and so on. But if you cannot write in this, the deviation of the state from this is large, then that's intrinsically tripartite.
Yeah.
So that contribution
The
is
idea is that you can distill that into a region B3, A3, B3, C3.
sorry.
You can somehow distill all the tripartite entanglement into A3, B3, C3.
No, it's more abstract than that. What they say is just the following: a state of this form you can show has this thing equal to 0 for either of the duals. Has 2EW equals I,
Okay.
right? And then they prove a continuity statement for either of those things, which says, imagine that I have a state that is close to this form, but is different. It has something else in it that is suppressed in G Newton in, say, rank as compared to this part of the state, right? So I have a state that's very close to looking like this, up to corrections in G Newton.
I'm just a little lost. You made a statement which
Yes.
And I
Oh,
don't understand
sorry.
why we didn't start with that definition.
Let me not say tripartite. Let me say non-bipartite. Okay?
But either way, we need the definition. And
Yes.
we need it for arbitrary states.
Yes, that's right. That's right. So the definition that Chris and Pratik give is they define what it means for a state to be entirely bipartite. Okay? And the way they define that is that it's some unitaries acting on a state like this. Right?
Which means they give us a class of states for which this is 0.
Yes. Right?
But we need more than that, right?
Absolutely. So they're going to prove the contrapositive of this statement. They're going to say, imagine that you have a state where the amount of non-bipartite entanglement is small.
But you haven't told us how to quantify that.
I'm going to tell you it means you're close to this state. I mean, I worry that this is like, I don't feel capable of giving you a good summary of the Akers-Rath proof off the top of my head. I will say that what they do is they add a piece of the state that is not of this form, could be anything, it's just not necessarily of this form, and that is parametrically small compared to this part of the state. Right? Parametrically small in G Newton. So they add something that is of a small dimension compared to the dimensions of these guys. Okay? And they show by a continuity argument that when you do that, this thing can't creep that much above 0.
So roughly speaking, if this quantity is 2EW minus I is big, like order 1 was in Newton, your state cannot be written in this factor form. So you have to put the chi A3, B3, C3. Namely, you have to partition A into A1, A2, and A3, and B into B1, B2, and B3, and C into C1, C2, and C3. So you need intrinsic tripartite chi A3, B3, C3, and that contribution, namely the size of A3, is significant compared with A1 and A2.
So what you care about is that the Hilbert space dimension of B3, A3 and B3.
Exactly, compared with A1 and A2. It's the same order in G Newton, 1 was in Newton.
That's right.
Or G Newton.
Thank you, Yasunari. That feel good, Raphael? Okay. If you didn't follow this discussion, I'll just tell you that there is a way of quantifying what we mean by non-bipartite entanglement that says whenever this thing is large in 1 over G Newton, then the amount of non-bipartite entanglement in the state is also large in 1 over G Newton. Okay? I encourage you, Chris and Pratik's paper is very easy to read. I encourage you to take a look at it if you're curious. It's, my own failure not being able to explain it on the spot, not theirs. Okay, so what this result tells us is that the difference between these two quantities, no matter which dictionary we take, the difference between these two quantities tells us something about multipartite entanglement. So what we do in our paper is we give some bounds on that quantity that I'm going to interpret for you using quantum information. So here's our work, or a part of it. It's sort of the main technical results of our work is going to be the following. It's a statement about pure ADS3 gravity, by which I mean three-dimensional ADS gravity where the metric is the only field. You don't add any other matter. We also only prove this for time-symmetric states, but I think we just weren't, I think it's not that hard to prove it for non-time symmetric states. We just didn't do it. So here's the bound. 2BW minus I is bigger than or equal to some universal constant, log 2 over 2. This constant comes from, it has to do with hyperbolic geometry. It's just some universal coefficient that appears in hyperbolic geometry, times the famous dimensionless parameter of ADS CFT, which is LADS over G Newton, times the size of the boundary of the entanglement wedge cross-section. And this is what I'm going to call the edge count. So what does this mean? Well, in 3 dimensions, oh dang, I erased my figures. In 3 dimensions, our entanglement wedge cross-sections are maybe like this, or maybe like this. These are the two examples I drew before. Right? The entanglement wedge cross-sections are going to be geodesic segments, right? And they're going to have endpoints. And so what I mean by the size of the boundary of the entanglement wedge cross-section is just going to be the number of those endpoints. Okay? So in both of these cases, the number of endpoints of the entanglement wedge cross-section is 2. 1, 2, 1, 2. Okay? But you can engineer manifolds where they have an arbitrary number of endpoints, however many you want. Okay? So let's return to an example that Raphael brought up earlier. Imagine we shrink A and B so that they're completely disconnected. Well, there's not going to be any entanglement wedge cross-section. It's going to be the empty set. So the size of its boundary is going to be 0. And the only bound I get in that case is that 2EW is bigger than or equal to I. But that's fine, because EW is going to be 0, and I is also going to be 0, because we're going to be in this disconnected phase.
Can it be more than 2? Can this number be more than 2?
Yeah, it can be any integer. Okay? You
to have like more boundaries and stuff.
Yeah. Well, you can actually just create. You can add very high topology things in the bulk, and I think create them that way. You might need A to be made up of a certain number of boundaries. I haven't thought about this in a little bit, but certainly by making like a large number of boundaries wormhole and making A half the boundaries and B some of the other boundaries, and adding a lot of higher genus stuff in the middle, you can make the integer whatever you want. Okay? So where does this bound come from? I'm not going to prove it for you. It's proved using techniques in hyperbolic geometry. And basically what we do is if you look up at how we wrote 2EW minus I there, we said it was a difference in area between two kinds of surfaces. This first parenthetical term up there has this like kinked surface minus the smooth surface, right? And the second term is also a kinked surface minus the smooth surface. And what we prove is a theorem in hyperbolic geometry about the difference in area between geodesics that are kinked and not kinked. And the total number of kinks gives you a sort of lower bound on how close you can get this thing to the area of a smooth geodesic with the same endpoints. It's an interesting proof. I encourage you to look at it if you're curious. I'll tell you about it another time if you're curious. I don't think it's going to be the right route for us right now. Okay? So what does this bound mean? I think it means something quite interesting already off the bat, which is that Akers-Roth told us that if 2EW minus I has an order 1 over G Newton contribution, then you have a large amount of non-bipartite entanglement, right? Now look over here. This tells us that as soon as we have a single edge in our entanglement wedge cross-section, we're going to have parametrically large 2EW minus I, and therefore we're going to have parametrically large non-bipartite entanglement. So what I want to say, I think this is a good heuristic that suggests to us that the structure of these edges, these corners, is emergent from non-bipartite entanglement. Okay? Now certainly that's true in the sense that if I have even one of them, I need to have non-bipartite entanglement. I would love it to be true that the more of these I have, the more non-bipartite entanglement I have. Unfortunately, we can't quite prove that because the measure of non-bipartite entanglement here was too coarse. It's just like, do you have a parametrically large amount of non-bipartite entanglement or not? So we can't know whether, if I have 4 endpoints, 2EW minus I is going to have to be 4 times as big as the lower bound is if I only had 1 endpoint. But we don't know if that means we have 4 times as much tripartite entanglement. Okay? These are our open questions. But heuristically at least, I think that we should interpret this as telling us that these codimension 3 features of the geometry, which are the boundaries of the cross-section, are really features that emerge from tripartite entanglement patterns.
Can I discuss how you prove this?
Why I think that?
How you showed it?
Oh, this proof?
Yeah.
Not more than like I said here, it has to do with proving a theorem in hyperbolic geometry on hyperbolic 2 manifolds. which is why you can only do this in a time-symmetric case, although I think it works for 3 manifolds as well, which is a theorem that if I have a curve that is made up of geodesic segments that meet at right-angle kinks, and it's homologous to a geodesic that is smooth, you can prove that the difference in area between those two is lower bounded by log 2 times the number of kinks. And the theorem, I mean,
Don't you need some other ingredient? I'm trying to understand this intuitively. I mean, if I take a geodesic and I deform it ever so slightly into, 3 segments with each geodesic that have side corners.
they won't have 90-degree corners.
One 90-degree corners.
Yeah.
Um,
Yeah. Here, Raphael, let me draw you a picture that might make you happy.
but why can't I make them? Oh, then they won't be geodesic.
Yeah. So here's like some big kinked geodesic,
Yeah.
and here's the proper geodesic that meets the same, that goes in the same place in the hyperbolic disk. What we do is that you can tile the homotopy region with right-angled pentagons. So I can do this, where each of these tiles is a right-angled pentagon. And then there's some hyperbolic trig about right-angled pentagons and the relative lengths of their sides.
Why do you? So, see, I'm confused about is that on short distances, ABS looks like a Minkowski space. What if I try to? What would be the analogous statement in a Minkowski space, and why can't I reach it? Like by just kicking on a short distance scale from ABS.
Well, you won't keep short distance scales, because if I keep kinking this geodesic, if I just keep kinking it on very short distance scales, yes, the kinks are happening on very short distance scales, but it's getting very far away from this smooth geodesic. Every kink I add brings it further and further away from the smooth geodesic. Also, if you kink the geodesic too many times too quickly, it's going to loop on itself and intersect.
Many times. Why would I want to do that?
What?
Just twice, right? I just need to introduce 2 corners.
But you wanted them to be very close to each other?
I think it would be useful to understand how the proof works. Right. I guess.
Well, why don't we talk about it at the end if there's time, or you and I can talk offline? Okay? The reason I didn't present the proof is because I don't think that our proof technique will generalize to higher dimensions, which is the thing I want to do next.
You're certainly using geodesic stuff from infinity or something, right? Otherwise, just this geodesic is the same.
No, you can actually have, like,
So you draw square.
imagine here's a part of a wormhole.
No, you draw square.
You can have like a geodesic, a kinked thing that goes like this, versus a geodesic that goes like this. So this is like a part of a wormhole. One of your kinked curves could be like this. It doesn't need to go all the way out to infinity. Maybe I think we should.
Say number is like a square, draw square, and this is geodesic. This is geodesic.
Right.
This has an edge, 2 of the edge.
Right.
And it goes this way. So L radius is infinity.
Right.
So 2 times infinity, it may go this way. But maybe in that case, it's quality or something, maybe infinity or something. It may not be, because quality is not defined, so it's just maybe fine.
John, is this sort of like an isoperimetric inequality or something that looks like that?
I don't know what that is, unfortunately.
I think, okay, yeah, I think we can have it. Yeah.
Okay, I would really like to. Well, I don't know. How long do we usually go? What's
For like 10 more minutes.
10 more minutes? Okay, I'm gonna have to. I'll abridge the end of the talk.
I think we can go a little longer. I mean, we ask a lot of questions in the Blackboard
Yeah.
talk.
Okay. Well, all right. Let me tell you a little bit about reflected entropy. I think it's good for people to know about. I think it's going to become more and more important over the next few years. So this quantity SR that I said was.
I thought you were going to tell us about the higher dimensional generalization of this, at least what the statement would be.
I was planning on doing that at the end.
Okay.
I think that probably, well, I erased things in a bad order, so unfortunately I'll tell you at the end. All right? Okay, so let's talk about the QI interpretation of our inequality, which I will rewrite over here. Okay. So, let me define for you reflected entropy. So reflected entropy is related to this thing called a canonical purification. It's a very beautiful story in holography. And the idea is, well, purification is the question of I have a density matrix. I want to add some degrees of freedom and entangle them with this density matrix in some way that I end up with a pure state that extends my density matrix. That's called a purification. So what is the most famous purification in quantum gravity? I would say it's the thermofield double, which purifies a thermal black hole. So let's remember how we get the thermofield double from a black hole. We start with the density matrix, which is 1 over some normalization factor, e to the minus beta h, right? And we can diagonalize that in the energy eigenbasis as sum e to the minus beta en, en, right? And then what do we do to get the thermofield double? Well, the first thing we do is we take the square root of this density matrix, which, because we've diagonalized it, is the same thing as taking the square root of all the coefficients. And then we just get tricky, and we flip this bra into a ket. And that's how we define the thermofield double. Okay? And it's easy to verify that the thermofield double is, in fact, a purification of the black hole. If I trace out one of these systems, I end up with the original density matrix. So what you can do is you can do this same procedure for any density matrix. For any density matrix that's diagonal in some basis, lambda j, jj, I can define a state psi rho, which is equal to sum over j square root lambda j, jj as kets. Okay? That's what we did in the thermofield double. It's going to be a purification of the state we started with. And because it's so simple, quantum information theorists call it the canonical purification. Okay. So why should we care about this in holography? Well, let's take a look at the geometric picture of what we did over here. Geometrically, how do we get from a one-sided black hole to the thermofield double? Right? The geometry of the thermal black hole looks like this. It's like a cutoff geometry where we have some boundary region R, and then we have a cutoff at the minimal surface, which is the position of the horizon. And that'll be gamma R. Right? What is the thermofield double state? Well, the thermofield double state is just the completion of that wormhole. So we have R, R prime, and the black hole horizon at the center. Cool. So what Dutta and Faulkner did in their paper was they generalized this. And they said that for any holographic row, taking the canonical purification looks the exact same as it does here. All you do is you reflect your space-time across the minimal surface. You double it. Okay? And they argue for this using the gravitational path integral. It's a very interesting argument. So as an example, let's look at our favorite wormhole state that we've been talking about. We have A, B, C, and here's our minimal surface gamma AB. The canonical purification is going to be constructed by taking this lower region of the wormhole and reflecting it across the minimal surface. So we get A prime, B prime, A, B. We have like a 4-boundary wormhole now with gamma AB in the center. Okay? So when we do this, let's ask what happens to our entanglement wedge cross-section, which was a curve like this. Okay? Well, when I reflect it, it ends up being a curve that loops the entire wormhole. And in particular, it ends up being exactly the Ryutaki-Nagi surface of AA prime. Okay? So from this, it should be obvious that S of AA prime is equal to 2EW, because it's twice the area over 4G Newton of the entanglement wedge cross-section. Okay? This is what Dunnett and Faulkner define to be the reflected entropy. All good on that argument? So I think, given time considerations, I'm going to skip. I'm going to abridge significantly what I had been planning on telling you. But I still want to give you the flavor of it, because I think it's interesting. We now have a formula for this thing called the reflected entropy. And we can study it as quantum information theorists, right? It is an entropy in a particular state. It's an entropy in this state called the canonical purification. Okay? So I will give you a theorem. And I'm not going to prove it in consideration of time, but I will try to interpret it for you. If I have any quantum state, then SR from A to B minus I from A to B is an upper bound on a very peculiar quantity that it's worth discussing. And I'll write it, and I think it'll look kind of insane at first, but we will make do. This is actually a very easy statement to prove if you know all of the right quantum information literature. Okay, so let me try to explain what this formula means. First, this F that appears in the middle is the quantum fidelity. It tells me how close two states are, right? So it's 1 if these two states are the same, and it's 0 if they're orthogonal. In the first argument, I've put the state on ABB prime. So that's like part of one of these holographic states up here. In the second, I've put something kind of funny. I've started with the state rho AB, and then I've acted with a quantum channel that only touches the B system. So heuristically, this is what we're doing. We know that there is some state on A, B, B prime. Okay?
B prime is the new C.
Hmm?
B prime is the new C.
Am I drawing this in?
Is B prime what you called C before?
No, B prime is in the canonical purification.
I'm sorry.
Yeah. So I have some state on ABB prime, which is a part of the canonical purification, right? And I know that there is some state on ABB prime, but I'm only handed the state on AB. And I want to do my best to try to make the full state, but I'm only allowed to act on B. So I can like add some correlations between B and B prime, but that's all I'm allowed to do. And I want to do as well as possible at reproducing the original state. So that's what this fidelity is. I act on AB with a quantum channel that only touches the B system. I'm trying to reproduce high fidelity with the original state, ABB prime, and I take a maximum over all such channels.
Why do you say that quantum channel touches only the B system, but you write it as B prime?
Yeah, it touches the B system, but it can add on it doesn't touch the A system is what I mean. I start with AB, and I act with a quantum channel from B to BB prime. B prime, like, when I start here, there's no B prime system. This channel adds in the B prime system and entangles it with the B system somehow. And I try to get back to a known state that's on all three. Okay? Yes?
John, all the quantities positive, right? Minus sign.
Yeah. When you work it all out, it all ends up being positive. Because the fidelity is between 0 and 1, so the log is between minus infinity and 0. So the minus sign makes it between 0 and infinity. Okay, so intuitively, I should be able to do this perfectly only if all of the correlations in this white state, in the actual state I want, if all of the correlations between A and B prime are somehow already there in the correlations between A and B. Right? I should be able to do some channel that spreads the correlations out between B and B prime, but it can't add any new correlations between A and B prime. Okay? All right. This is a theorem in quantum information theory. I'm just going to draw a picture that I think will make it very sort of clear and interesting in holography. But the point I want to make is that if this quantity is small, what that means is that I can do this recovery quite well. Whereas if I know a priori that there is some obstruction to doing this recovery, that's going to tell me that this quantity is going to be large. Okay? That's the way that this inequality works. So what I'm going to argue for you is that every boundary in the entanglement wedge cross-section makes this process harder and therefore drives this quantity up. And that's what I'm going to give as the heuristic explanation for our bound up there. Right? I think this will be very quick at this point. I'm just going to draw. Oh, also, in our paper, we call this quantity the Markov gap. And the reason for that is that such a process is called a Markov recovery process, because it's like a Markov chain. I go from A to B, and then I try to go from B to B prime. I'm only allowed to touch B. I'm not allowed to touch A. It's like a Markov chain. OK, so I'm just going to draw a picture. Actually, I'm going to use this. No, I'm going to redraw this. OK, let's think in holography again about our favorite canonical purification, which is the one I already drew up there, which is the canonical purification of a three-boundary wormhole, of two boundaries of a three-boundary wormhole. Okay? So here is gamma AB. Here is gamma AA prime. And here, this is going to be important, is gamma ABB prime. Okay. So let's think about what this recovery process is telling us to do. The state we're trying to reproduce is almost the entirety of this spacetime. It's everything from the bottom right here all the way up to this surface, right? It's the entanglement wedge of A, B, and B prime all taken together. But the state we're given is just the lower half of this picture. We're given the AB entanglement wedge. And we're allowed to act only on B. Okay? So it seems like an impossible task. You certainly won't be able to do this in general. But I'm going to identify one obstruction for you that I think is really fundamentally important, which is the boundary entanglement supporting this surface. Okay? So let's think about this surface, which is the part of gamma AB that lies on the A side of the entanglement wedge. Okay? We have this intuition in holography that connections across bulk surfaces are sourced by boundary entanglement. So I want to ask you, where is the entanglement that sources the connection across this surface? Right? Well, it can't be in AB, because this surface is, if I take any tubular neighborhood of this surface, it's not going to be contained in AB. It's going to spill over, right? That geometric connection is on the boundary of AB, right? It's also not in BB prime, right? The BB prime entanglement wedge is the right half of this picture. So everything going across that surface has to come from somewhere else. And so the heuristic I want to give you is that the entanglement in the boundary sourcing that connection forms a fundamental obstruction to doing this recovery process. This is not supposed to be rigorous. I'm really just trying to give you a heuristic here, right? This isn't in AB, and it isn't in BB prime. So certainly, if I start with AB, and I act only on B, I'm not going to ever be able to create this entanglement. Okay? Now, where are the endpoints of this surface? They are exactly the boundaries of the entanglement wedge cross-section. So what I want to suggest to you is that, if I tweak the moduli of this spacetime, I can shrink the actual size of this green surface as much as I want. But at the end of the day, I'm never going to be able to get rid of those endpoints. Those endpoints are always going to be there. So I want to suggest to you, I can change the relative size of the throats of the wormholes so that this neck becomes arbitrarily small, and the length of the green surface can be whatever I want it to be. I'm talking about different kinds of states, right? There's a family of states of pair of pants geometries where I tweak the various lengths of the wormhole mass. Right?
You're not talking about that.
No. I'm talking about looking at different kinds of states and asking how they're entangled. Right? So even if the length of this green surface were to be very small, those corners would still be there. And what I want to suggest is that those corners represent the entanglement sourcing those corners is entanglement that's never going to be able to be reproduced in this process, and therefore is going to have to contribute to this quantity SR minus I. And that's one way that I'd like to interpret the inequality I wrote up there. That those corners are sourcing or are sourced by some entanglement that is just never going to be visible to a process like this.
Why is it not the length of the green curve?
What?
Why is it the corners and not the length of the green curve? I don't understand.
I don't know. So this is what I'm trying to give here is an interpretation of this inequality. So we start by knowing this inequality, right? And then we write down all of sort of the quantum information things we can. And we end up, I think, very naturally being led to consider the entanglement across this surface as a fundamental contribution to SR minus I. Okay? And so I want to connect these two stories in a non-rigorous but heuristic way by saying the fact that this surface is an obstruction to SR minus I being 0, and the fact that we know mathematically that the true obstruction comes from the endpoints makes me want to think that the true obstruction here is somehow from the endpoints. Those are the things that are irreducible. That's the part of the surface we can never get rid of, no matter how small we shrink its length.
So this is a lower bound, that's the point.
Yes.
Even if you just try to do it.
Even if this, yeah,
Minimal amount,
that's right.
and that says lower bound of Tripartite encrypted. So if three P's A, B, C need to be connected,
That's right.
signaled by this existence of this dot,
That's right.
then that means you need the intrinsically tripartite.
That's right. That's
Otherwise,
right.
it's probably superposition of A, B connected to C far away, B, C connected to negative far.
Yeah.
Something. You need to have three mouse wormhole. They need to be ZX, whatever. Just intrinsically tripartite.
I think this is probably actually, in consideration of time, I think probably we should stop the recording here. I'm happy to keep talking about it and answering questions if people want to stay, but for now, thank you for your attention.
More questions, or Jon, do you want to say more things?
Higher dimensional generalization.
Yeah, so I haven't generalized it to higher dimensions, but I can guess at what it might be. This is the last line of my abstract. I said I'd speculate wildly. So this inequality, 2EW minus I is bigger than or equal to some constant times the size of the boundary. You could imagine that that exact same thing is true in higher dimensions. Only now, the entanglement wedge cross-section, let's think about 4 dimensions, right? The entanglement wedge cross-section is codimension 2, so it's some 2-dimensional thing. So its boundary is 1-dimensional. So the size of that boundary might be replaced by the length, right? So I think it's possible that in every dimension we'll have some universal dimension-dependent constant times a codimension 3 volume.
Is it obvious that it's, I mean, there would have been a sort of fork in the road here where it said, I'm still just counting how many components,
Mm-hmm.
no matter what
Yeah.
the length. Is that obviously wrong? Is that
No.
something-
I don't think it's obviously wrong. Well, maybe I might be able to construct examples where I think I can probably actually construct examples where you have a non-trivial component, but this thing is very small.
Do you have any idea what the pre-factor is?
No idea. So in the paper, what we did was to sort of try to guess at this, we took a couple of simple examples of like families of states in ADS4, where you can compute the left side very simply. And we minimized it in all of those different classes. So we minimized 2EW minus I, and we looked for, divided by the boundary length, and we looked for a universal constant. And in all the families, we ended up with something different. So, with these, the situation is pretty subtle. We weren't able to find any bound that way. Yeah, yes, Nora.
Is there anything interesting? Usually this entanglement of purification or defect entropy measures the correlation, total correlation between A and B, including classical
Absolutely.
and quantum.
Mm-hmm.
And neutral information in the context of holographic state is mostly just the quantum correlation.
Mm-hmm.
Okay? Not in general, but in the holographic.
Right.
So this seems to be saying that if you have A and B connected to C space-time because you have this your dot,
Mm-hmm.
then A and B has to have significant classical correlation because that's probably something you measure by 2 times E W minus I.
I think.
Is there anything interesting from that statement?
Well, it's an interesting proposal. The thing is, I don't think we know enough about this reflected entropy to know whether that's right or not. For example, mutual information measures both quantum and classical correlations. And we know that in holography it's mostly quantum. This is what you said. But just because it's only seeing quantum correlations doesn't mean it's seeing all of the kinds of quantum correlations. So it's possible that this SR quantity, maybe it's bigger than I because it's seeing quantum correlations that I is not seeing, right? Or possibly, like you said, it's seeing classical correlations that I is not seeing.
So we don't.
Yeah, I think we don't know. I mean, there's a. I think that there's good reason to study this SR just in quantum mechanics, right? Try to understand what it means.
It's possible to be
Yeah.
fully quantum.
Right. Right.
Yeah, maybe because it's kind of Z type-ish correlation, sound right? Maybe between ABC.
Yeah. So actually, GHZ has the special case where they're the same. In GHZ, SR and I are equal.
Okay, GHZ is so special.
Yeah, right. There are other kinds of things where, yeah, exactly.
Yeah, but anyway, that's your message,
Yeah.
We can't. A priori.
Oh yes, okay.
So this is, you're saying bipartite versus multipartite. Is it possible or useful to think about like something within multipartite, like I don't know, like we were talking earlier about tripartite, whether that can be precisely defined. Can you like break up multipartite further?
Yeah, so Kai's question was, can we break up multipartite entanglement further? I talked about bipartite entanglement, and then I talked about multipartite entanglement, and once or twice I said the words tripartite entanglement. And the answer is yes. The answer is, you can talk about k-partite entanglement for any integer k. As long as I'm only ever, splitting my boundary into 3 regions, I'm really only going to see tripartite features, right? But I can define things that, I can subdivide my boundary into a lot more regions and study things and look for higher party things. Some people from Berkeley, I think, actually have spent quite a lot of time on this. At least Ning Bao has, with some collaborators, have started to ask these questions of like, if I choose a huge number of boundary components and I try to study simple geometric quantities, am I going to see things that might signal features of higher party entanglement? But I will tell you that actually, purely in quantum information theory, the theory of multipartite entanglement is very underdeveloped. It is something that is, really hard and is understood still understood by me at least at a pretty basic level. And I think that the field is actually still very much in progress.
Any more questions for Jon? Yeah, also Jon is around, so follow up.
Yeah, I'll be here for the rest of the year. So.
So yeah, thank you, Jon.